Okay, I think I'm going to go ahead and get started. Can you guys hear me? Okay. Yeah, okay. Okay, so last week we started, hold on a second, sorry. Okay, so last week we were looking at um, kind of momentum and impulse. And so we found a couple relationships, and we didn't finish whiteboarding the lab responses and kind of go over the answers, and that's kind of what we're going to do today. So let me share my screen with you. Oh, wait a second, there's somebody. Hold on a second, sorry. I think there's somebody. I don't know who Paco is, so sorry, they're going to have to try again with a different name. Okay, so we had two labs that we're kind of looking at: Impulsive Force Lab and the Explosion Lab. We looked at the graphical mathematical models, and kind of what I would like to do today is whiteboard the rest of the um, lab response to make sure you understand the answers. And then the goal is at the end of the day, you'll know what, or at the end of the class, you'll know what the answers are for this lab response, and then you can turn it in. As far as turning in, if you want to work together in your groups, normal groups, and then just simply like share a folder that has all your names on it for the lab response. You could sketch, or maybe you could upload pictures, whatever's easier for you. If you got it printed out already and you've done it by hand and it's easier for you just to simply send me a picture of the lab response on your cell phone, that's fine. You can do it that way. But in that case, if that's the way you do it, then you're only doing it for yourself, and you're not doing it for everybody in your lab group, okay? Because I know you're not with other people in your lab group. If you want to just simply share the whiteboards with me, everybody's contributed, and you got your names up here at the top, and you could just make one file. Please don't send me a email for every whiteboard, but you can put them all in one file, and you can send that to me and share that with me with all your names on it. And I know that everybody in that group will get those points in for that lab response. Again, it shouldn't be groups any bigger than three students or 2 or 3 students. It's totally up to you. You do what you want. Okay. And that's not due though. Let's see. What did I say? That's due. Um, before the next Zoom meeting. Next Zoom meeting would be on Wednesday at 9:20. So whenever you can do it right after this class if you want to, or you can do it before the next one. That's fine too. Okay, so we've already looked at the graphical models. What I'd like to do is kind of whiteboard 15 through 19 and then the other problems as well. So how about I give you a few minutes to work on 15 through 19. If I remember correct, I think those are the true false maybe. So why don't you work on those for a few minutes, and then if somebody wants to share those with me, just tell me, and I'm hoping that I can just stop sharing and you can show your whiteboard then. Okay? All right, so I'll give you a few minutes to work.
What if we're already done with all these questions?
All done. Just maybe be patient here for a second, and then we're going to display it just to make sure. You want to know for sure if your answers are right before you turn it in.
Yeah, I just didn't know if you wanted us to redo them. That's what I was worried
Only if you think they're wrong. Yeah.
about. All right.
Yep. Anybody need more time on those true false? Oh, somebody want to share their screen? All you have to do is go at the very bottom down there. There's a green button that says share screen, and then you click on it, and then you'll click the blue share screen, and we should be able to see your whiteboard then. So it's kind of like you're presenting your whiteboard to us. Quicker somebody does that, the quicker we're done.
All right, I can do it if you want.
Yeah, go ahead and share your screen. And yeah, just those, yeah, that one right. I think if you just double click on it, maybe. Is it not working?
Yeah, I don't know why.
Huh. That's weird. I think we can maybe see it. Maybe, I don't know. I don't know.
I mean, it's true, false, 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 true.
Okay, so the first one, I think it says momentum is a scalar quantity. Is that what it says, scalar? Or no,
Yeah.
vector?
Momentum is a vector quantity. And
Vector quantity. Okay, so that means momentum has direction, and I think we all agree with that, right? Thumbs up? Yeah, okay. Change in momentum is a scalar quantity.
That's false.
That's false. That would be an impulse, which has direction as well. So that's false.
And then the next one was false, and that's that impulse. Well, no, that's change in momentum is a scalar quantity.
Right. So change of momentum is the same thing as impulse. So really 16 and 17 are asking the same questions. So neither one of those is scalar. They both have direction. So they're both vector quantities. So yeah, I think I agree with those. Those are both false. And then number 18, that symbol again would mean the impulse. The impulse is the same thing as momentum. Yeah, that's not true. Impulse is really the same thing as a change in momentum. So that's kind of number 19. So I think I agree with that. Everybody agree? Good? All right, nice. Okay, so I'll take control again. Thank you very much, JJ, for sharing. Okay, the next one we're going to be doing is number 20, which looks like this. So when you're doing this one, could you please don't just put the answer down because it says show calculation. Just maybe it's hard to draw that symbol. Maybe it's not the easiest thing to draw the integration symbol. If you don't want to draw the integration symbol, just simply go like integration of f dt, something like that. So go ahead and do number 20. I'll give you a couple minutes to do that. Does anybody need more time? Can we have somebody different maybe share? Again, the faster we share, then the faster we're done. And it's okay if it's wrong because that's why we're whiteboarding. Chaitanya, thank you. So Chaitanya, can you talk? Unmute yourself. Can't hear you. Make sure like let's see, F4 on your keyboard. Okay.
Yeah.
Okay, so kind of walk us through how you went about solving this.
So momentum is mass times velocity. So I just did the initial momentum minus the final momentum.
Okay.
And I got 15 kilograms meters.
Almost perfect. Almost perfect. Everything you said is really great. So you had to find the initial momentum. You had to do the final momentum. There was only one slight mistake, and that is that whenever you're finding a change, it's always final minus initial. So it really would have been 0 minus the 15, and so you get like a negative.
Yeah.
What do you think that negative 15 kilograms times meters per second means? What does the negative mean, do you think?
I think it's like going in the opposite direction.
Yeah, so if you read through the problem, it says to the right. So when you get that negative, that just means it has this impulse to the left. So the answer would be 15 kilograms times meters per second to the left. All right, I'm going to take control. Thank you very much, Chaitanya. I really appreciate it. So let's see. So for this one, I hope that you can see my screen for this. Yeah, that integral f dt, that's just simply equal to change in momentum. It's easy for me to write it out in words. Change in momentum. And to solve that, that would just simply be the final momentum, pf, minus the initial momentum, pi, which would be equal to, let's see, it's going to be 1.5 times 0 minus 1.5 times 10. And so, yeah, you end up getting a negative, and we have to translate what that negative means. So you get a negative 15 kilograms times meters per second. But really what that means is 15 kilograms times meters per second to the left. Any questions? Are we all good? All good? Okay. The next one we're going to look at then is number 21. And number 21 kind of goes along with number 20. So we already know what the impulse is. We just calculated it. And so now what you're doing in number 21 is calculating for the force. So why don't you go ahead and take a couple minutes to solve that one, number 21.
So what was the number for the last one? Like the number of the problem?
It was, oh, what problem was it? It was problem, I think it was number 20, but let me check here again, sorry. That was number 20. The last one was number 21. The last one was number 20. Now we're getting ready to do number 21.
Okay, thank you.
Yep. Okay, I think that one's a little bit easier. Somebody want to share their whiteboard? Again, where you share, as you go down to the bottom, you see the little green arrow. It says share. You click on that, and then you click on the blue pop-up that says share. The quicker we get this shared, the quicker we're done. Vlad, thank you, Vlad. Okay, so can you talk, Vlad? If you hit your F4 key, I think that'll turn on your microphone. Oh, not able. I'm not hearing Vlad. Okay, so I think I'm going to talk. Oh, Vlad is. There you are. Yeah,
Good.
there you go. Yeah, can you explain what you did here?
Yeah, so force by time, which is impulse, equals that's m change in v. I forgot to put the delta
Right,
sign.
right.
So impulse equals the change in momentum. So the force by the time, and we have that change in momentum, and we just find the force, which is 150 newtons.
Perfect. Perfect. I have one slight thing I need to add, and that is because it's a vector, we need a direction. And it would be the same direction as the change of momentum. So it's to the left. Yeah, that's the only thing. So it's 150 newtons to the left. Any questions from anybody? All good? All good? Okay. All right. Thank you very much for Vlad. Appreciate it. Okay, so the next one we're going to do is number 22. And I think this is a separate problem here. So we have a different mass and, and force and all kinds of stuff. And we're just trying to figure out what the final velocity is, assuming it came from rest. So I'll let you go ahead and solve this one, give you a couple minutes, right? Anybody want to share their whiteboard? Again, sooner we get it shared out, the quicker we're done.
I think I could do it.
Sure, go ahead and take control. At the bottom, hit share screen, and then the blue pop up or another screen pops up, and hit the blue button. Okay, here's Brett's. Okay, and you want to kind of walk us through how you solved it?
Yeah, so I noticed that there seemed to be a constant of variation along with the velocity and impulse model.
Okay,
And when I used the units, it looked like it was 1/kilograms. And I found that it was the constant was 1/mass. So the mass was 5 kilograms. So if you look in this area down here, I'm not sure if you can see my cursor.
okay,
It was 1/5 because it was 1/5 kilograms times 20 newtons times 1.2 seconds, which is 4.8 meters per second.
okay. Yeah, that's totally, I think in this one, we found out the ratio of the velocities was equal to the negative inverse of the ratio of the masses, and that was totally true. And so what we found from that is we defined this new term called momentum. So I'm going to go ahead and take control back because I actually did a little bit different, but we get the same answer. And I kind of want to share with you mine. So again, I think I'm going to start off with just reviewing what that model was. It was velocity of the red divided by the velocity of the blue was equal to negative mass of the blue over mass of the red. And I said that I didn't really want to deal with any kind of ratios, and so we rewrote this as velocity of the red times the mass of the red equals the negative mass of the blue times the velocity of the blue. And we went a little bit further and we actually called this new thing of mass times the velocity, we called that momentum. So it was the momentum of the red was equal to negative momentum of the blue. And I think I probably should draw a little picture here to explain. We had this car that was red. It was kind of going in one direction. They were kind of exploding away from one another. And you had this other car that was blue, it was going in the other direction. And their relative speeds kind of depend upon how much mass or inertia they had. So we also said, you know, what was the momentum? If momentum is mass times velocity, what was the momentum before the explosion? And I think everybody said, well, the momentum of either one of them would be 0. And so we actually did this a little bit different. We said, well, we went a little bit further, I should say. We said that they would have the same force on them because of Newton's third law. If I had you draw a force diagram right during the collision, or not the collision, the explosion, they would have, let's say there'd be a force on the red from the blue, there would be an equal and opposite force on the blue from the red. And so that led to this idea of impulse. Force times time equals mvf minus mvi. In fact, we'll kind of see that in the next lab we're getting ready to whiteboard. So anyway, for this one here, what I did was I set up that equation right up here at the top, and I plugged in the force and the time, and I just did mvf minus mvi, the initial velocity is 0, and we get the exact same speed. Okay, so you can do it with ratios, or you can do it with this equation that we're going to kind of see in the next lab too, that we're getting ready to whiteboard. The only thing that I would add to yours, Brett, was you really ought to put a direction in there, and the direction would be to the left. That's the only thing. Okay. All right, so the next one, number 23, kind of looks like this. So I would suggest, if you can, try to use this equation because we're going to use that quite a bit. So for number 23, try to use that equation. The ratios is fine too, that will work as well. But I think this equation here will help us a little bit more. So why don't you go ahead and see if you can do that one. I'll give you about 2 or 3 minutes. Okay. Excuse me. Anybody want to share their screen? If you need more time, that's fine. I'd like to have somebody different, not anybody that's shared already, okay?
my screen this time?
Yeah, go ahead. It's at the bottom. There's a little green share, and then click that, and a pop-up will come up and hit the little blue share.
Okay. So for this one, we did the final minus initial to get the change in momentum.
Cool.
And then we did 1.5 times negative 10 minus 1.5 times 10. We got negative 30. So then we knew that was 30 kilograms meters per second to the left.
Perfect. Yeah. And so this is kind of interesting. I'll go ahead and take control. That looked perfect to me. So let's see. This is kind of interesting because usually, whoops, I'm on the wrong one, sorry. Usually when you think of something that bounces, sometimes people are thinking, oh, that's, you know, that's more gentle. Let's say it has some big long spring or something. I don't know if I can even draw a spring. So let's say there's a spring here, it bounces into this wall. There we go. And so we have this object that's moving toward this spring. It's going to bounce off the spring, and then it's going to come back the other direction. And some people are usually thinking, oh, that, you know, that'd be a kind of gentle force or whatever, but it ends up being a pretty big one, because if, let's see if I can copy this, put it right over here, stop. Sorry. It's not going to let me do it. Oh, there it is. If it would have just simply come to rest, so the final speed would be, let's say, 0. Whoops, I have to change this stuff. So the force times time, which is the impulse, and the impulse is equal to change of momentum. If the final velocity would have been 0, so it would have been 0 minus 1.5 times 10, you'd actually only get 15. Compared to this, which is 1.5 times negative 10, then minus 1.5 times, you end up getting 30. So the impulse, J, the impulse, is much bigger when there's bouncing. That's one of the reasons why for your car, they put the headrest so your head doesn't bounce and get whiplash. It's a bigger force whenever you have bouncing. So anyway, very good, nice. And yeah, I do need a direction. I forgot or no, I don't need, it doesn't tell me a direction, so I can't put a direction. I guess I could say in negative direction for this one. Or I could say backwards or something. All right, good. Okay, so then the next one, number 24. So, oh, in fact, I kind of gave you the answer, I guess, for this one, but you think about it for a second. So, and then we'll share it here in a second. Anybody want to share their answer? Somebody different? This would be one that might be easier just to say instead of writing it all out. I mean, when you turn it in for a lab, you can write it all out, but. Everybody staying safe? Have you ever been to, what's it called? Chain of Lakes? Chain of Lakes, yeah. I just went on, when was it, Saturday, I think it was. It was free, you could go there. It's a nice place if you like going out in the woods and stuff. It's not too far away. It's really big. It's away from all the roads and everything. I'd recommend it. It's not too many people there. Anybody want to share their thinking on this one? Somebody different? Well, maybe we'll do it this way then. Maybe this would be easier to do all together. How about you guys unmute yourself? It says, Johnny says that bumper cars are safer because the impulse, that symbol means impulse again, experienced by an occupant is less than that experienced by someone just hitting and coming to a stop. In other words, it's safer to bounce because the impulse is less. What do you think? What do you guys think?
Well, kind of like what you said in the last problem.
So
When it bounces, it actually doubles.
right, and so is Johnny right or wrong?
He's incorrect.
Yeah, he's incorrect. So yeah, he's wrong, and the reason is because when you're looking at MVF minus MVI, since it's a vector, you're not going to do mass times 10 minus mass times 10 because one of those 10s is in the opposite direction, so it's going to be a negative. So you're actually adding instead of subtracting. So I think that would be the correction. So Johnny's thinking that, okay, mass times 10, let's say it's going in at 10 meters per second, it bounces at 10. And so he's thinking mass times 10 minus mass times 10 is going to be 0. Well, that's not true because one of those velocities is going to be negative 10, not positive 10. So it's going to be mass times negative 10 minus mass times 10, and you're going to get a bigger impulse. That's his mistake, that he's forgetting that it's a vector. Okay, so we're done with that one, that lab. You should be able to send me your lab then, either just share the whole folder with me when you get it all whiteboarded, or if you want to print it out, take a picture and send it to me. Okay, so the next one is going to be the Impulsive lab. We already have the mathematical models. Wait a second, did I do the wrong one? Yeah, we did this one, didn't I? I did it out of order, dang it. Sorry about that. Too early in the morning. Let's try that again. Explosion lab. So I did it out of order. I apologize for that. Okay, so we already did the mathematical models for the explosion lab. Now I know why you guys were a little confused. Sorry about that. Let's see. You know, I think this one's going to be pretty fast to whiteboard. I don't know that we're going to actually whiteboard this. How about we just discuss this? So what this was, it was the two cars were kind of bouncing away from one another, whereas the impulse lab, the one we were just getting done with, that wasn't there where they're bouncing away from one. What that was the astronaut that was moving. Sorry about that, kind of messed up. So this is the cars that were kind of shooting away from one another. What would you predict would happen if they had the exact same mass? How would their final speeds compare to one another? What do you guys think? Just unmute yourself.
Same.
Yeah, the same, right? But what if it says, now I'm going to change the question. Actually, I'm going to use the question they have here. So I asked you speeds, but now let's say we're not saying speeds, we're going to say velocities. How would the velocities compare?
Same but opposite, like negative.
Exactly. It's kind of reminding you of kind of Newton's third law, right? It's just the same magnitude but in opposite directions, right? Okay. And why is the reason for that? What do you think they would have the same? Think about. I'm sorry. Say it again. Why?
They're the exact same mass and they
They're,
have like equal force. Yeah.
Nice. Yeah. They have the equal force and they have the same mass. So therefore, they're going to have the same final exit speed, right? Okay. If in fact, let's say you did the lab in class. Unfortunately, you weren't able to do it in class. But let's say you did it in class and you got this track here. and you've got two cars. One's blue and one's red. So here's the red one, and it's shooting off this way. And you got the blue one, and it's shooting off this way. Hopefully they look about the same size. We're gonna say they're the same mass. Huh, can't get them exactly. There we go. And it turns out when you do this, they don't have the same speed. Let's say the blue one's slower. They have the exact same mass though. Okay, so here's a mass M, and this is also mass M. If I can copy and paste it. So they have the exact same mass. Can you think of anything in the lab that might explain that? Why they might not have the exact same speed? I'm sorry, I interrupted you. Sorry. What?
No, that's fine. The distance from the explosion is like different. Like one could be farther away from it, and one could.
Ah, okay. Yeah. Unfortunately, it's hard to do this because. Actually, wait a second. Hold on. I want to see if I can show you the video again. Let's see. Where was it? I thought I had a video of explaining in the lab. Yeah, I don't remember where it's at now, sorry. The truth was these two objects, when you shoot them away from one another in lab, the reason why they're shooting away from one another is because there's this little plunger. It's not like you have a chemical explosion. So imagine this little spring-operated plunger that pushes off of one another. That's what it was. If you can remember, I triggered something and they kind of shot away from one another. So they really weren't the same. They weren't different distances. They were really right up against one another. But the truth is, when you do it in the lab, almost never do you get the exact same speed, even though the masses are the same. Can you think of things in the lab that might cause it not to have the same speed?
Inclined surface.
Yeah, that's the biggest problem. It turns out that this ramp a lot of times is a little bit at an incline. And so we have to adjust that as best we can. Sometimes it looks like it's perfectly level and still the speed isn't the same. Can you think of any outside forces that might be affecting it?
Friction?
Yeah, there might be a little bit more friction on one car than the other car, just depending upon the wheels or something. So anyway, all right, so that's that question. Number 19. Oh, I don't want to whiteboard this one either. In the two fragment explosion that results when you fire a gun. So let's see if I can, actually, I think I'll just look on the web for a cartoon, can't spell, cartoon gun. See if I can find one. There we go. All right, so let's see if I can copy and paste this, snip. All right, okay, so here's my gun. I'll go ahead and draw that, edit, copy. Oh, this thing's constantly in my way. Sorry about that. All right, so here's my gun, and we have this bullet that's coming out. So let's say this is my bullet that's being shot out of it. The question is, in this explosion that happens, why is it that the bullet has so much faster speed than the gun? The gun actually does move too. The gun moves backwards. I'm not sure if you've ever shot a gun before, but it does kind of, we call that recoil. It kind of recoils, it shoots backward a little bit, kind of kicks backward. The question is, why is it that the bullet acquires so much bigger speed than the gun? What do you guys think?
The mass.
Yeah, it's the mass of it. So let's say we design a new gun, like, you know, they're always coming up with new designs for stuff. Let's say we have a gun and it shoots out a bullet that has exactly the same mass as the gun. How would the speed of the bullet compare to the speed of the recoil if they had the exact same mass?
It would be the same.
It'd be the what? I'm sorry, you got cut out.
It would be the same.
It'd be the same, that's right. So however much recoil there is, there'd be the same amount of speed on the bullet too. That would be the exact same amount. Hopefully it looks about the same. Okay, so any questions on number 19 there? No. Okay, and let's see, number 20. I don't even think I want to do 20 because we weren't able to go. Yeah, we couldn't do this in lab. So that one's, I think, is a little bit too hard since we couldn't do it in lab. So for this second lab, you do not need to do number 20. You can leave that off, okay? All right, so then let's come back to today. Oops, I got to go to the calendar for today. Sorry. All right, so I would like you to send me your lab responses before the next Zoom meeting on Wednesday. So you can do that anytime before then. Worksheet 1, I think I shared with you. Please don't make copies of worksheet 1. So let's see if I can find worksheet 1. Let's see. So I've made groups already so that you can actually come in here, and I'm trying to make it so you can actually do the whiteboards. What I want to try to do on Wednesday, or as we're whiteboarding those, is I found, I sat in on a class at Purdue Fort Wayne, how this physics professor was doing it. There's this thing called Discord. I don't really know anything about Discord a whole lot, other than you can use it to actually talk to one another. So imagine you had the whiteboard pulled up, this one here, and you can work together on it, and you could use Discord to kind of talk on at the same time. So I'm trying to see if I can figure out a way to make that work for us, to make it more like real classroom on Wednesday, okay? So before you go though, I need to share with you the attendance quiz code. So I would like you to take a quiz kind of over the stuff we just whiteboarded. And the code for that is, here's the code. Lowercase YT, uppercase NCC, lowercase EK, hashtag lowercase v. And I think there's 5 questions. There's 5 questions. Okay, any questions? Okay, so that's it then for today. And then I'll see you at 9:20 then on Wednesday. And again, just make sure I get those labs. You don't have to do worksheet 1 ahead of time. In fact, I'd really rather you didn't. If you're going to do worksheet 1, that's fine. Please don't do it all. So in your whiteboarding groups, I don't want one person to do a whole whiteboard. I want you to I want you to work together on the whiteboards. I want you to talk, just like in classroom, as much as possible anyway, or chat or something, okay? So if you don't get to it, that's fine. All right, that's it. So see you later. Bye.